Okay, this is video 3 in the sequence of videos for chapter 23 on geometric optics. This video will be on the index of refraction and Snell's law. Let's go ahead and begin. In general, light slows somewhat when traveling through a medium. And we might ask ourselves the question, why? Well, let's start by looking at how fast light can travel in a vacuum. If we had, pull out a little picture here, if we had some astronauts maybe traveling between the Earth and Mars, they might come across a speed limit sign posted between these two planets. Speed limit 299,792,458 meters per second. That happens to be the speed of light in a vacuum, and it's the fastest anything can travel, at least as far as we know. So we would call that value c. It's the speed of light in a vacuum, about 2.997. Let's see, it looks like it's 2.9979 times 10 to the 8th meters per second, and that would be the speed of light in a vacuum. As far as we know, that's the maximum speed anything can travel. Now, when light travels through something of substance, like maybe air or water or diamond, it does slow down. And let's see if we can figure out why that is. Let's go ahead and pull up this simulation here. And there we go. Here I have a little light source currently turned off. We've got a carbon monoxide molecule that we're going to go ahead and shine some light on. Now, carbon monoxide, it's a carbon and an oxygen atom. They're sort of bonded. It looks like a triple covalent bond. And let's go ahead and turn on a light source. Now, the recording software that I'm using is not doesn't have quite a very high sampling rate, so it might be hard to see all of the animations here. We have a photon of light, so this simulation is using the particle nature of light to sort of show what's happening here. So this infrared photon, sometimes it's being absorbed by the carbon monoxide molecule. Now, this model is sort of showing the molecule sort of at an excited energy state, sort of going back and forth when it's absorbed that photon. That's sort of like the electron being kicked up to a higher energy level. It's an excited state, and then eventually when the electron sort of falls back down to a lower energy state, it sort of re-emits that photon, and you can see oftentimes that photon that's re-emitted is sort of pushed off in some random direction, so maybe a sort of a scattering effect. Now, if we consider that light might be traveling through a bunch of different types of molecules, that every time light gets absorbed by one of these molecules, it sort of takes some time for it to sort of decay back down to a lower energy state and sort of kick that photon back out. So if we go back to our picture here, we might consider maybe these astronauts here. Maybe they have to make a pit stop. Maybe there's a rest area that they have to stop at for a minute, and then once they get back into their spacecraft and take off again, it takes a little bit of time for that to occur. And that's maybe the way that we can think of light sort of slowing down when it travels through substance, some sort of substance where it must be absorbed and then re-emitted. So a lot of that is due to a decrease in speed, is due to absorption and re-emission. So the index of refraction of the medium is the ratio of the speed of light in vacuum to the speed of light in that medium. So we're going to go ahead and consider now this thing that we define as the index of refraction. We have an equation we can write for that, and the index of refraction is equal to c over v. Now, this ratio would always be greater than 1. Since c is the speed of light in a vacuum, that's the fastest we can ever have. The speed of light through some other substance must be slower than that. When we take the ratio, n would always be bigger than 1 for anything other than a vacuum, for all media. Okay, so it's going to be a value greater than 1. Now, these things over here, you can see air, 1.0003. Well, that's almost the index of refraction for a vacuum. What that means is that light travels almost the same speed through air as it does through a vacuum. Now, when you consider water, it travels slower yet. When you go all the way down here to diamond, we can see that light travels fairly slow through a diamond, 2.42 times slower than it does through a vacuum. So it gives us a sense of relative speed, or how quickly light can travel through that substance. Let's go ahead and try a couple of problems here. How fast does light travel in plexiglass? Well, n for plexiglass is 1.51. I want to find the velocity of light through plexiglass. So let's go ahead and write that as Vp. That would be equal to c over n for plexiglass. So be careful there, with V being in the denominator. Got to bring that over here. N would go back into the denominator, and we can go ahead and write that as 3. I'm going to use just one sig figure. 3 times 10 to the 8th meters per second divided by 1.51, the index of refraction for plexiglass, and we get about 2 times 10 to the 8th meters per second. So we've reduced the speed from 3 times 10 to the 8th to 2 times 10 to the 8th meters per second. How does the speed of light in water compare to the speed of light in diamond? Well, let's go ahead and do this as an actual ratio. So we're doing a comparison. Let's go ahead and write that comparison like this. The speed of light in water compared to the speed of light in diamond. So let's go ahead and do that. Well, I can write that as a ratio of, sort of like I did over here, I could say that's C divided by N in water, and then divide that by C divided by N in diamond. Well, you can see the C's reduce out here. And we could write that as, let's see, I've got a fraction within a fraction. VW over VD would be equal to ND over NW. And see, diamond is 2.42 times slower than light in a vacuum. Water, the speed is 1.33 times slower than light, speed of light in a vacuum. And what we get for that is about 1.82. Now, that ratio, number 1.82, basically tells us that light travels through water 1.82 times faster than it does through diamond. So, key summary on this slide here: the index of refraction, a ratio of the speed of light in a vacuum to the speed of light through a substance. Now, this is related very strongly to refraction of light. Now, you may remember refraction, we studied it in our wave unit. This is the bending of light, or change in direction of any kind of wavefront as it passes from one medium into another. Recall that a wave's frequency is fixed. It's a constant value. It depends on what the source is. But the wavelength will change when its speed changes. Now, if we have, again, some sort of wavefront, could be water, could be light, could be sound, that's traveling from a slow medium to a fast medium, and it hits it sort of perpendicularly to the normal, what we would see is no change in direction, but we would see a change in the wavelength due to the fact that the speed has changed. Okay, so the wavelength has increased in proportion with the speed. Now, if I go from fast to slow, you would see the wavelength decrease. Okay, so when we talk about a wavefront changing from one medium to another medium and it strikes at an angle, this is where we start to see refraction. Okay, and we did, as a quick review here, we did sort of talk about like maybe soldiers walking arm in arm as they travel from a fast to a slow medium. This portion of the line of soldiers would sort of lag behind a little bit if we wanted to think of it like that. Overall, we would see an overall change in direction of the way that this wave is traveling. Okay, and so since this sort of gets hard to draw, we often just use, again, that ray model of light. So we would consider maybe a normal line here. We might draw a ray coming in, so this might be the incident ray. That would be the incident angle. And then, let's see, as it passes through that interface into this new medium, we can see that the direction of that light has changed. Remember, the direction of the velocity is always perpendicular to the wavefront, and so you can see that this angle, which we would call theta sub r, is less than theta sub I, so it's sort of bent towards the normal, and the opposite would occur if we were going the other way. So this one, since this is a faster medium, this portion of the wavefront would probably get in front of that, if you will, and so now we would see that the wave is sort of bending away from the normal. Okay, and so again, with the normal line here, go ahead and draw something like that here, and we have an incident angle and we have a refracted angle. Okay, and so this one is sort of bending away. Now, what's this theta prime here? Let's see, theta I, theta r, we might say those are incident and refraction angles. Theta prime is an angle of reflection. Remember, anytime we travel between two media of different propagation speeds, we're going to get at least some portion of that wave will reflect. And when it reflects, we would call that angle theta prime. Angle of incidence is equal to angle of reflection. So we'd get some portion of the wave reflecting, some portion refracting. Okay, so on this next slide, we look at how we might combine some ideas now of the index of refraction, sort of a new topic for us, and this idea of refraction. Refraction is what makes objects half submerged in water look odd. This woman's legs will appear shorter. The pencil appears to be broken here. Let's see if we can understand why that is. If we come over here to the picture of the beach here, we have some light that is coming off of that woman's foot. That light is traveling this way. It goes from water to air. Now, if you remember the indices of refraction here, water is about 1.33, air is about 1.003. So light's going to actually speed up as it goes out of water into air. So that means it bends away from the normal. Now, we believe light travels in a straight line, so even though her foot is down here, the person on the beach would see her foot higher up. Makes her legs look a little shorter. This pencil is actually a continuous pencil. The fact that it looks broken is simply because light refracts as it exits water and goes into air. Now, the angle of refraction depends on the indices of refraction and is given by Snell's law. So it really depends not only on the change in speed that it experiences, but also the angle at which that incident ray sort of enters that new medium. Remember in chapter 11 that we formulated an equation for refraction using something that looked like this. V1 is to V2 as the sine of the angle that that wave front makes with the normal in that first medium compared to the sine of the angle that that wave front would make with the normal in the second medium. So we sort of wrote it like that. Now if we do a little cross multiplying here, you would see V1 sine theta 2 is equal to V2 sine theta 1. Let's see if we can't write it in terms of n now. You may recall in the previous slide we said since n was equal to c over v, we could say v is equal to c over n. So let's go ahead and write that here. So this would be c all over n1 times the sine of theta 2 would equal c all over n2 sine theta 1. We can see that these sort of reduce out. And if I want to bring the n2 over to this side and the n1 over to that side, we would then get the statement that we have here. So n2 sine theta 2 is equal to n1 sine theta 1. So this is really just a reformulation of the equation that we developed in chapter 11, now done with the index of refraction. Okay, so there we go. That is Snell's law. Let's go ahead and put that to use in a couple of examples here. So from this point on, if you feel like you have the core content down, you don't necessarily have to watch these videos, but these are going to be on applying those concepts to a few examples. Okay, so let's begin. Light incident in air passes into calm water an angle of 25 degrees to the normal. What is the angle between the reflected ray and the refracted ray? So let's draw a little picture here. Let's see, here's my air-water interface. And I've got a light beam coming in here that strikes the interface at an angle of 25.4 degrees from the normal. And let's see, air, it slows down when it travels from air into water, so it's going to be bending toward the normal. And let's see, I could find this to be theta r if this is theta I. The question is actually asking what is the angle between the reflected and refracted ray. So we also have a reflected ray that goes this way. We call that theta prime. Well, that's easy to get. That's 25.4 degrees, right? Angle of incidence is equal to angle of reflection. Now for this one, we're going to find theta r using Snell's law. So ni sine theta I is equal to nr sine theta r. I'm looking for the angle theta r, so let's just rewrite that for sine of theta r is equal to the sine of theta I times ni over nr. And let's go ahead and start plugging in some numbers here. the sine of 25.4 degrees divided or multiplied by the index of refraction of air. Well, that was 1.0003. And for water, that's 1.33. So when I go through and solve that for r, theta r, I get 18.8 degrees. Now that's not the answer to my question. I'm really looking for this angle, right? So I'm looking for that. So I need to find the complements here. If that's 25.4 degrees, this angle here would be 64.6 degrees, and if I found that angle as a complement of this, that would be 70. Looks like 71.2 degrees, and so my overall angle, the angle for that bigger arc, would be 64.6 plus 71.2, or about 136 degrees. Okay, so that's what we'll call that one. Let's take a look at number 2 here. Light in air shines through the side of an aquarium made of crown glass that's 35 centimeters thick, enters into a pool of water. If the light strikes at an angle 55 degrees from the normal, what is the angle of the refracted ray into water? Let's go ahead and draw a little picture for this one too. So we have some crown glass, and it's pretty thick crown glass, so it must be a pretty good sized aquarium. Here we have air, here we have crown glass, and here we have water. So we really have 3 different media, so 2 different interfaces along which we'll have some refracted light. So let's go ahead and put green in here. So here we have maybe a ray of light traveling this way. I said it was 55 degrees from the normal. When it goes from air into crown glass, well, I know air is 1.0003. Crown glass, I could look that up in the previous tables, so 1.52. In water, that one I sort of memorized, 1.33. Light slows down when it goes from air to crown glass quite a bit, actually. There's a big change there, so it's going to bend. Light slows down when it goes from air into crown glass quite a bit, actually, and I know that from the large difference in the indices of refraction, so it's going to bend quite a bit, and so I'm looking for that angle. I'm going to call that theta r. Now, when it travels through the crown glass, it will refract again when it goes into water. Now in this case, let's see, 1.52, it's reducing an index of refraction. Remember, the bigger the number, the slower the speed of light. So this is actually going to speed up as it goes into water, and so now it's going to bend away from the normal. My eventual answer is to try to find this angle. I need to use some color coding here so that I don't mix up these different theta r's. So I'm going to go ahead and draw this as a black ray, and then I'm going to draw this one as a blue ray. Okay, so we can sort of keep track of those using some color coding. Okay, let's go ahead and try to find theta r here. So Ni sine theta I is equal to Nr sine theta r. I'm looking for theta r again. I'm going to use the same kind of setup that I had up here. So I'm just going to come back and look at that equation. Already went through all the algebra to get to this. So the sine of theta r would be equal to the sine of the incident angle, that's 55 degrees, multiplied by the ratio of those indices. Well, in this case, my incident angle, or incident index of refraction is 1.0003. My refracted is 1.52. And I get for that angle, for theta r, I get that to be, it looks like about 32.6 degrees. Okay, so that would be this angle. Now, when I go to do this next one, I'm going to switch this over to blue. Here, when I go to find theta r here, I'm going to recognize sort of like an alternate interior angle idea, that this would be theta incident now for the new light ray. So this angle here, theta r, becomes my incident angle for the next interface. So I'm going to be trying to find, again, theta r here. So the sine of theta r is equal to the sine of my incident angle. So again, I'm going back to this version of that equation. That incident angle is 32.6. And the ratio of those indices, again, remember, is from the incident to the refracted. So now this would be 1.52 to 1.33. And when I calculate theta r here, I get a number of 38 degrees. Okay, so its angle of refraction here, 38 degrees. Now, I want to stand back and look at this for a second, evaluate these answers. You notice that I'm going from air to ground glass to water. I've got two different interfaces. Those interfaces are parallel to each other. If it went from air to ground glass back to air, I should expect this angle, 38, to be the same as what it had coming in. It would refract equally, just in opposite directions, from the normal when it goes from the same kind of medium from one to glass back to the same kind of medium. Here, you notice that it's going into water. So these angles are no longer the same. If I were to look at a fish that's in here, so I have some fish over in here, and I had light coming off of there, they're going to appear to be in a different direction or different location than I would see them over here, simply because of that refraction. Okay, and I have one more problem for us to look at here. So a submarine at a depth of 78.5 meters and 145 meters from the shore shines a laser light angle of 28 degrees from the vertical. The laser strikes the top of the building located on the shore. What is the height of the building? So if you're ever in a submarine and you need to determine the height of a building along the shore, this might be a way to do it. Okay, so let's start with a picture here. So let's see, I have no idea how to draw a submarine, so let's make it a yellow submarine. Let's see, not fair that you guys might have to trace this yourself, so I'm going to go ahead and draw this here. And so, and let's see if I did that, how that looks. So there we go. There's our yellow submarine. It's at a certain depth of 78.5 meters. So here we have some water surface here. So it's currently at a depth of, looks like 78.5 meters. Let's shorten that just a little bit. And so let's see, 78.5 meter depth. And we're going to shine a laser light. Let's use a red laser for this one. And we're going to shine it 28 degrees from the vertical. And so that would be a 28 degree incident angle. So this is water, and this is air, and so that's going to bend away from the normal. Now it happens to hit the top of a building that's located right along the shore. So let me just extend this just a little bit. Here I have the shore. Probably doesn't have an abrupt edge like that, and for some reason they placed the building right on the edge of that shore. Probably difficult to get a permit to do such things. Okay, and so that laser light then comes up and it just strikes that building right there. Looks like I gotta put an addition on that building. There we go. Nice little drawing for us. So what I'm looking for is the height of that building, and so H is what I'm looking for. Well, let's see, a little bit of stuff going on here. Let's see, they told us it was 145 meters from the shore, so it looks like I have this distance is 145 meters. Okay, and a quick plan of approach here, plan of attack. Looks like I'm going to try to find this angle, theta r, from the using Snell's law, and I can find the complement of that using just to find that angle using the complement. If I can find that length, which it looks like I might be able to do by sort of coming down here and figuring out that length, I think I can get to that height using a series of steps. Let's go ahead and first try to find theta r. So again, going back to the Snell's law, Ni sine theta I is equal to Nr sine theta r. Same kind of solution I've had before, so I should recognize this. And let's just go ahead and plug in some of those numbers. The sine of my incident angle, here's 28 degrees. The indices of refraction, Ni is my water, that's 1.33. The air, 1.0003. That will give me, when I go through all that math, I get an angle of 30, looks like about 38.6 degrees for that angle. Okay, so let's place that there. The complement of that, this would be 51.4 degrees. Now all I really need to do is try to find this length, and I can use sort of a tangent function to find that height. So how could I find that length? Looks like if I come down here, use some right angle trigonometry to find this, let's see, so if this is 78.5 meters, I could use a tangent function. So the tangent of 28 is equal to the opposite, and so I just call that opposite divided by the adjacent 78.5, and so the opposite, which is what I'm looking for, 78.5 times the tangent of 28, that I get about 41.7 meters. Okay, so if this is 41.7 and this entire thing is 145, this would be 145 minus 41.7, and that is about 103 meters. So this distance here, about 103 meters. There we go. Now I just have a simple right angle trigonometry problem here. This is 103. This angle was at 51.4. I'm looking for height. So the tangent of 51.4 equal to the height over 103. So the height 103, tangent of 51.4, and for that we get a height of, looks like about 129 meters tall. So there we go. A few examples of how we might incorporate a new concept called the index of refraction with something sort of that we talked about before, refraction, but we got to combine that with Snell's law, and hopefully this set of slides helped you understand those concepts.